Alright guys, today we're gonna go back to logarithm, however in new updated base 10. Alright, so logarithm with the base 10 is commonly called common logarithm. So common logarithm with the base 10. Okay, so that's simply normal one, except for we didn't put 10 as the base. And when we write in log, let's say x, it means that the base is 10. However, we don't write the base. In this case, we assume that the base is 10. So log 10 of some number x. Okay, so we actually can take as the function, and in this case we simply erase 10, and in this case we mentioned that the base of 10. Alright, so what's the main property for that? So that's actually normal log, except for we can apply to have the following tricks. For example, let's say we have a number and we take number as 10 to different powers. Let's say 10 to the power of 1, 10 squared, 10 cubed, and so on. So let's write this number as the power of 10. So it's already written here, number as a power of 10. Okay, we've written that, and now we're taking the log of the number. Let's take the log with the base 10 of a number. So let's say we have log from 10 to the power of 1. According to the basic property of the logarithm, see my rules for logarithm and try to watch this video if you're new here. So we simply take the power in front of log. So in this case, we simply can write log 10, and what it means? It means 1, right? Because with the base 10 and log 10 of 10 is 1. You can check using calculator. Okay, so let's check 10 squared. In this case, we'll have log with the base 10, 10 squared. According to the property, we'll get log with the base 10 and of the number 10 times 2. In this case, we'll get 2. So simply, if we apply the log, you understand the logic that you taking the power and put it just in front of, because log with the base 10 of a number 10 is always 1. Okay, so make sure you understand. Let's practice with fractional powers. There was actually number 10, 100, 1000, and so on. You just keep going this row. All right, what about fractional powers? In this case, we'll get the square root of something, and we'll take the square root of 10, square root of 100, and probably square root of 1000. What will happen in this case? All right, so let's see what we've got if we use the power notation. So in index form, we'll get 10 to the power 1 over 2. In this case, we'll get 100 to the power 1 over 2. However, it will be 10 squared, and to the power 1 over 2, just 10. Okay, and here we'll get 1000 to the power 1 over 2, but 1010 cubed, so we'll get 10 to the power 3 over 2. And again, if we write the log of the number, we'll get the following. Here we'll get log with the base 10, 10 and 1 over 2. That's simply 1 over 2. Here we'll get log 10 of 10 to the power 1, which is 1, right? And here we can get the log of with the base 10 over 1000 to the power 1 over 2, but I write as 10 3 over 2. So we'll get the power. Okay, so you notice that we can figure out if we have 10 to some power, we can easily figure out the root of and the power of corresponding number. That's how it works. So sometimes it might be useful in order to, let's say, using the main property of the logarithm, a to the power. So we can write a as 10 to the power log with the base 10 of a, right? Because as you remember, 10 to the power log 10, because the same base is here, we just simply get a, right? And hence we're eligible to do that. Okay, so what if your number is, let's say, a equals 2? So what can we write in this case if we apply a log of 2? So we apply log a to both sides with the base 10, we'll get the following. Now we can calculate using your calculator. We can approximately calculate log with the base 10 of 2. So everyone has like standard button key. So just press log 10 of number 2, and we find out that it's about like 0.301. So I round up to 3 dp. Okay, in this case, I've taken only 3 digits after the decimal point. Okay, so in this case, we can figure out using the property that it's going to be your a as 10 to the power log a. In our case, a is 2, so we simply can plug that and write that 2 is about 10 to the power 0.301. Okay, that's also a useful thing if you want to convert and represent as 10 to some power. Okay, so what about if we take number and multiply by 10? So we take a, which is 2, and then we multiply both sides by 10. So we've got another number, let's say b, which is equal to 20, or simply is 10 times a. What if we apply the same property and try to calculate log of 20? So we'll get round, use a calculator, we'll get 1.301 round, or just approximately. Okay, so what we can do now, we simply can say that 20 is, using the property again for logs, is 10 to the power 1.301. Cool stuff. All right, so we can use any number and present as 10 to some power. That's interesting stuff. What about rules for logarithm with the base 10? It works the same. For example, we can consider some rules and just simply apply the same logic as if your base is general a. So for example, log for, let's say, a times b, it's going to be the sum of logs. However, we use base of 10. Okay, the same logic as for general logarithm. Okay, for division, a over b, we have a subtraction of logs. So we simply can write as log with the base 10a minus log with the base 10b. So you understand that it works pretty the same. Okay, so probably you might be wondering as how to write, I don't know, let's say we can try practicing and go to logarithmic equation, but before we just consider like several cases. For example, we have some y represented through a and b. Let's say a is to the power 5 and b squared. Can we write this expression in logarithmic form? So basically try to convert into logarithmic equation right now with the base 10. So that's log with the base 10. And we just simply need to write this into logarithmic form. Okay, so for both sides, we just apply log with the base 10, and we'll get the following: log of a5 and b squared. So what we can do right now, we just apply logarithmic properties as for normal logarithm, and in this case, we can get log y equals to, so here we'll have multiplication, and that's why we'll get log a5 plus log b squared. And then how to simplify it to have like two logs, we simply can write log y equals to 5 log a plus 2 log b. Okay, So what's the powerful of these methods if we use, instead of like powers, we use simply linear form of logarithm? So it allows us to set up a proper, graph which is linear, for example, for more complicated function. All right. So what it means, if we explore dependency y from a and from b, let's say from two parameters, as in this case, so you obviously see that y from a dependent as a5 and y from b is dependent as b squared. So it's pretty much more complicated. And if this was obtained, like if you're trying to figure out this by having experimental data, you can do better the following. So you can convert it into logarithmic statement. And now we see that log y is a linear combination of log a and log b. So simply you can say that it's going to be a linear combination of log a and log b. Okay, so more real example. Let's say we know that your mass, according to the formula, is just simply density multiplied by the volume. And for like spherical object, like for a sphere, we know that volume is 4/3 pi r cube. All right, so what we can do here, instead of exploring mass from r cube as cubic dependency, right, from m mass from r, sorry, as cubic dependency, we better use logarithm from both sides. Okay, let's see how it works. That's density and this is volume, right? So what we can use the formula 4/3 pi. Density we include here, and we still need to times r cubed. So actually that's cubic dependency. However, if we get experimental data, it's much better to use the line of best fit for that. And hence, instead of using that, we can simply apply logs, right? So what if we apply log with base 10 to both sides? We'll get a following. We'll get log m is simply log of 4/3 pi times the density. And here I separate it with r cube. Okay, it's much better to use the following. Log m equals to, using the property of multiplication, I consider this as just coefficient, as some number that if you know the density. And I'll get log of 4/3 pi density. And simply because I've separated using the log properties, I just add simply 3 log r. Okay? Now we see that log m, if it's a function of r, so simply it's a function of log r. And this case is straight line. So it means if you plot log m versus log r, you'll get simply a straight line that goes through y-intercept, which is log 4/3 pi times density, and with the gradient of 3 because it's the coefficient before log r. It's much better because you can use the line of best fit in this case. If you have experimental data, let's assume your log m and log r is simply like points. And actually, it's much better to use straight line dependency instead of the original one, which is cubic. All right? You see how logs can be applied, for example, in experimental analysis when you want to handle your data. Okay? And guys, hopefully, I think it's pretty like short topic that we consider first absolute mass, and then we also consider application, what usage might be using logarithm and where you can apply that. So make sure you understand that. This is the topic of definitely like applied maths or even GCSE first maths. So make sure you guys understand how it works. And in the next video, we'll go through logarithmic equations. That's a very interesting topic, and of course that's sort of GCSE extended and also first maths GCSE. So make sure you're in touch with me. Don't forget to subscribe. Don't forget to share the video for anyone who's interested in maths and GCSE preparation or general math preparation. Just drop the comments with the questions you're interested in. Feel free to contact with me. No problem. You'll get a feedback immediately. So you Daniel Dallas. Hope you enjoy. Peace.